Hello and welcome to our lesson on cracking. Okay, so a quick recap then. Which of these, A, B or C, has the strongest intermolecular, or I should say strongest really, the most intermolecular forces between it and another chain like it? Well, hopefully you would recognise it's A. And will A have a high or a low boiling point? Well, hopefully you would recognise that A, being that longer chain, has a high boiling point. So will it condense at the top or the bottom of the fractionating column? Well, it will condense at the bottom of the fractionating column. And if you got that question wrong, you're not alone. It's easy to get it muddled up. You've got to get it in your heads. The long chains are near the bottom. The short chains will be at the top. Okay, so let's see if we can match up the name of the hydrocarbon fraction and what it's used for. So, petrol, what's that used for? Which picture? Hopefully you recognise it's the car. That's the easy one. Okay, bitumen. Okay, so bitumen is the tarmac on the road. It's a very long chain, hydrocarbon, very sticky. That's what it's used for. Kerosene. Kerosene is aircraft fuel. Diesel. That's more likely to be your lorry. Yes, we have cars that are diesel, but it tends to be more the lorries. Lubricating oil. That's going to be this picture here. So lubricating oil in your car engine to stop the metallic parts rubbing together and rubbing away. Chemicals, so things like naphtha, all sorts of things. I've used lighter fuel here, but all sorts of things, including in perfumes and in makeup products and stuff like that. Loads of different chemicals from hydrocarbon fuels. And fuel oil, well, that's your big ships and the stuff that tends to leak when they leak oil in the sea. That tends to be the fuel oil. So all these products coming from crude oil, and of course we haven't mentioned plastic yet. We'll come on to that. But all these products come from crude oil, and the petrochemical industry, that is the industry that deals with crude oil, digging it up, finding it, digging it up, processing it, refining it, getting it out there, is massive business. It's a big business. And the reason it's big business is because it's used in almost everything that we do. If you look at that list there, everything on that list we're almost using almost on a daily basis. Even if you're not driving a truck, you will use something today that has arrived at the shop on a truck that you've then bought. And it all comes from crude oil, and we know that crude oil is finite, it's going to run out. So when we carry out fractional distillation, for some reason, it's just the way it's formed, there are always more long chains than short chains. So we always end up with lots of long chains near the bottom, and we end up with fewer short chains, the petrol, the naphtha, the refinery gas. That's a problem because we use a lot more of the refinery gas, the petrol, the naphtha, the kerosene. We use a lot of that, whereas we don't use as much fuel oil and bitumen. We do use it, but not as much. And we've actually got more than we need of this and not enough of this. So this is about so supply and demand. We have a short supply of these short chain hydrocarbons, but we've got a high demand, and that's why we end up with higher prices. So what are we going to do then? How can we solve this problem? Well, here's a long chain hydrocarbon. It's not that long, I suppose. Hydrocarbons can go up to 60 carbons, but it won't fit on my page. What can I do? I've got a long chain. I don't need it. I need short chains. Well, hopefully you recognise I could just split it up, and then I've got two short chains. Yes? And this is called cracking. Okay, so cracking is the technical term where we take a large hydrocarbon molecule that we don't need, we put it in a cracker, which is the machine, and out pops short chains that we can use. Now, the temperature we need for breaking these up is between 400 and 700 degrees. I guess that depends on the size of the hydrocarbon going in. Obviously, the longer it is, the more energy you would need to break it. We're going to use a relatively low pressure, so about 70 atmospheres. It's a moderate pressure. So ATM is atmospheres and that's the pressure. So we're going to apply a bit more pressure. We know that speeds up a chemical reaction. And we're going to use a catalyst to speed up the reaction as well. We're going to use aluminium oxide. And you'll notice, or at least I would like you to notice, if I counted up how many hydrocarbons I've got here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons there, I should end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons there. So I'm not creating anything, I'm not destroying anything. I've got the same number before and after, they've just split up. And you'll notice this one's split up into different things. It's actually split up into alkanes, which is your petrol, and some alkenes, which are the double bonds here. Okay, so here's another long hydrocarbon being split up. You'll notice each time I end up with an alkane with the single bonds, and I always end up with a double bond, and that's because I don't have enough hydrogens to make this fully saturated. So they end up double bonding because there's not enough hydrogens to go around. So you'll always end up with at least one alkane and at least one alkene, though it could be more. This one here, this is actually the same hydrocarbon. This is still decane. It's just split up in a different way. So this time I've ended up with pentane, which is a fuel. I would use that as a fuel. And then I've ended up with propene and I've ended up with ethene. Now, the alkanes are then we use as fuels, and the alkenes, those double bonds, we actually what we call polymerize into plastics. So they go into another process, polymerization, which you don't need to know the details of, but they become the plastics, the polymers. Okay, again, here is decane again. This time it's separated into octene with the 8 and the ethene with the 2. And what I'm trying to do here is just show you that in an exam question, they might give you a hydrocarbon and just check how it's going to split. So they're probably going to give you one of them and then you would have to finish off the other one. Or they might tell you to draw it and they'll say one is 8 and one is 2. So just be careful. You will end up with the same number of carbons and hydrogens before and after, but it can split in different ways. Okay, guys, what I would say, last little thing then, just remember that the alkanes, those single bonds, become fuels, and then the double bonds, the alkenes, become polymers or plastics. Okay, that is the end of this lesson, guys. Thank you.